Okay. In order to explain this particular transformation, I'm going to take you back to, let's say, f of x equals x cubed. We all remember this graph, correct? We committed this graph to memory. How does it look? How does x cubed look? Anyone remembers x cubed?
So it's in the first and third quadrant.
Very good. It's an odd function. And I was mentioning that notice the difference between this cross and this cross. We're going to talk about this in chapter 3, but I want to give you the heads up. Very important. So this is indeed x cubed. Now, let's suppose I want to determine a function that is g of x, but g of x is f of twice x. So f has x in it, but here it has twice x. So what did I do to x? I multiplied it by 2. Perfect. So when we talk about multiplying or dividing x, so what do we remember from the previous 5? When I add and subtract 2x and from x, I do this. Yeah, I forgot to tell you, it's a drill at 2:15. And the phone may ring also. Maybe that's it. Okay. So the same thing here. When I change x into double x or 1/2 x or 4x, it's also a horizontal change. Every time we talk about a change in x, we're talking about a horizontal change. When we talk about a vertical change, we're talking about y change, correct? Okay, so this was multiplied, so 2 times x. Now, can anyone tell us how to determine f of twice x having this function? I'm given x cubed, I want to find f of twice x. What do I have to write? How do I evaluate the function? This time for 2x.
Plug in 2x for x.
Awesome. All I have to do is just take this and plug it in. Perfect. That's how we evaluate. So I would have to put parentheses, and what do I get? Inside,
2x.
perfect, and very good. Awesome. So this, I'll continue here, and I'm going to graph the whole thing again. So how do I raise 2x to the third power? This is not a binomial. I do not obtain 3 terms. This is just one product. So what do I have to write? How do we raise 2x to the third power? Perfect, which is 8 times, awesome, times to the, exactly, good. So let's go back and look at this and analyze this together. Forget about the answer for a moment. What did we do? We changed x into twice x. Now forget about all this, and let's see what we got. Let's analyze this. This is a transformation that we talked about. It's among those 5. So this is x cubed. When I have 8x cubed, do I do this? Or from x cubed, I do this? What does 8 in front do? Does it vertical shrinking of the graph or vertical stretching of the graph by a factor of 8? But I'm not dividing heights. I'm multiplying all heights by 8. So from this, which is x cubed, I get 8x cubed. Agreed? Okay, so let's think again one more time, because this is the most difficult transformation. That's why I wanted to leave it for next time, for next test. So I replace x by twice x. But the result was, what happens to x? Just analyze what happens to x. So when I multiply x by 2, horizontal by a factor of, careful, 1/2. Let's do it again. That's why this is the most difficult one. Everything else is straightforward. This is not straightforward. Okay, one more time. So this is x cubed. I'm changing x into twice x. I get this result, which does this to the graph of the function. What happens to x? Is it doubled or halved? One more time. This is the original graph, and this is what I come up with. What happens to x? I divide it by 2. So every time, so that's our conclusion. And we're going to look at an example in a minute. But I need to explain both of them. So this is basically a horizontal shrinking, oops, by a factor of 2. Well, I'm sorry. Of course, I meant to write 1/2. Of course. So twice x, one more time, twice x, if you want to look, I know I look silly, but maybe this will trigger your memory. Twice x does not do this. Twice x does this. Okay?
Half x to the other thing.
Yes. All x values are divided by 2. So then I'm asking you now, so let's graph to see the transformation. So this is the base function, which is x cubed. And the function twice with x replaced by 2x is this. This is twice x, everything cubed. That's why it turns into a horizontal shrinking by a factor of 1/2. And I'm sure you got the idea. So if I ask you now, this is f of x, which is x cubed, but now I want f equals 1/2 x. I don't have to go through the steps again. I know exactly what this is going to do. It cannot do this. This was already taken. So it will do exactly the opposite that you would expect. So this is a horizontal stretching of the graph by a factor of indeed 2. Let's look at a couple of examples, and then we can move on. So they are on page 2.5. If you want, I'll let you choose whatever you want. I'll just point them out to you. Yes. 33 through 44. 33 through 44. So let's take a look and see which one would be exactly what we discussed right now. From that set and this set, just choose.
40.
Let's take a look at 40. It's 1/2 f of x minus 2. No, we're not changing x into 3x or 1/2 x. It's outside. This number 1/2 or negative 1/2 does not touch x. If it's outside, it changes what?
So it would be like 43.
43. Perfect. Because f is applied to twice x. 43 is a perfect example. Let's choose one more. 44. Okay. Also 49, right? Also 50. Okay? So which ones? Please dictate, and we'll work on those. 43. And let's say for different function, 43. And let's say also 50. Okay, so let's look at 43 and 50. In 43, we're asked to find g of x, which is 1/2 f of twice x. We're given a graph of the function f. So here it is. I'm going to copy it. I see a point at -4, 0. 1, 2, 3, 4. I see a point at 1, -2. And it's a straight line. And then I see a point at 0, 0, full point, and 1 at 4, -2. Full point. So here's the graph. And what we see here is function f. We're asked to use the graph of y equals f of x to graph each function g. First, I have to list the transformations. What will be the first transformation that I have to perform here? Remember, it has to be in order of operations. So the base function is f, and the first transformation is on f. Yes, f of twice x. What will that do? When we change x into twice x, do we do this or we do this? Yes, so we divide all x values by 2. Okay, so let's do that. So this is at -4, -3, -2, -1, 1, 2, 3, 4. Ready? So this point has x -2. In order to graph f of twice x, where do I move this point? Very good, awesome, right here. This point has x equals 0. Where will it go? Exactly, nowhere. So I have the first piece done. This point is at x equals 0. Where will it go? Nowhere. And this point is, I can do more, but I don't need more than a few points. So this point is when x is 4. Where will it go? Yes, it will stay on the same y altitude. I cannot change that. So it goes here. So here's the graph. So this is the graph of f twice x. Okay, we have one more transformation. Let's identify the second transformation now. The second transformation is on function from part 1. So what would be that last transformation? Anything else but changing x into twice x or x into 1/3 x is straightforward. This is the only one that sounds or looks backwards. Okay, so what happens now? How do I graph this from the graph of this function? This is gone. I don't have that anymore. So this is f of twice x. What do I have to do in order to graph this? Exactly. Dividing them by 2. Very good. This point, let me use blue. So this point is at y equals 0. Where will it go? Good. This point is at y equals -2. Where will it go? Very good. -2 divided by 2 is -1. So this is the first piece, and it's done. This point is at 0, 0. Where will it go when I divide its y value by 2? Nowhere. This point has y equals -2, but I have to divide that height by 2. Where will it go? So here's the graph. So this, of course, and this as well, is 1/2 f of twice x. So first we did what? We used horizontal shrinking by a factor of 1/2, and then we used vertical shrinking by a factor of 1/2. Anything else here? Should we do another? Should we look at another problem or we move on? Any opinion? No opinion?
We can do one more problem.
Of course. So let's say 49. We have g of x equals twice f of 1/2 x. And here's the graph of f. Let's graph it together. Not a difficult graph. So I see a point at -4, -2, right here. I see a point at -2, 0. I see one at 2, 0, 0, 2, one at 2, 2, and one at 4, 0. So this is the graph of f. As you see, we have a little bit of difficulty illustrating this particular transformation, horizontal shrinking and stretching, with any particular function per se. So we're given a graph to illustrate it. Okay? And when you ever decide to take trigonometry, this will be extremely helpful. And we have lots of functions in which we can illustrate this transformation, but not per se in algebra. Okay, what is the first transformation? Number 1. Yes, so this is f of 1/2 x. I should have written it here. So it's a horizontal shrinking of the graph by a factor of 1/2. And this is a vertical shrinking, also by a factor of 1/2. Good. So what will this do to the graph of f when I change x into 1/2 x? Exactly. So this will be a horizontal stretching by a factor of 2. And then the next one will be the transformation on the first one. So it's the 2 outside. What will that do? Yes, which is a vertical. Yes, by a factor of 2. Okay, let's do just that. So first you told me to stretch the graph by a factor of 2. This is a transformation in x. So here's the point. This is at -4. This point has x -4. Where will it go? Very good. 6, 7, 8. Right here. This point has x equals -2. Where will it go? That's it. This point has x equals 0. Where will it go? Perfect. This point has x equals 2. Where will it go? And this is at x equals 4. Where will it go? So here's the graph. This is the graph of f of 1/2 x. Now we apply the last transformation. Let's do that. Okay, so this is a transformation in y. The y value of this point is -2. Where will it go? Very good. This point has a y value of 0. Where will it go? This point has a y value of 2. Very good. This point has a y value of 2. We'll go to 4. And this point has a y value, a y coordinate of 0. Where will it go? So here's the graph. This graph is 1/2. No. This graph, sorry, I'm going to erase that, is twice f of 1/2 x. Any questions on this transformation? As I said, it's I didn't want to spend too much time, and I really needed some time to explain this, so I didn't want to include it in this test. Okay, moving forward, section 2.6 is a review. However, I'm going to present everything that is in it. The next one is based on 2.6. It deals with inverse functions. And the last section of this chapter is distance in the midpoint formula and the circle. Okay? So let's continue with 2.6. I'm hoping that in about 2 to 3 weeks, we should have our second test. Hopefully before the end of October. Okay? So 2.6 deals with few things. One, it is called Algebra of Functions. By algebra, we mean we add, subtract, multiply, and divide functions. That's the algebra. The second topic is function composition. Which is a totally different idea. The notation for function composition would be this. It's a little circle of x. Okay? What does this section deal with? It gives us two functions, and we're asked to create new functions from the given functions. How? By adding, subtracting, multiplying, and dividing, or by function composition. So let's start with, please give me two functions of your choice so we can illustrate, and I'll refresh your memory on adding, subtracting, multiplying, and dividing functions. You can choose if you'd like. They are on page 310, or we can choose, or we can make them up. Anyone wants to make two functions up? No. Okay. So let's say 3x squared plus 2x minus 7. And 2x minus 4. What type of functions are these? The biggest umbrella, the umbrella over both of them is polynomial. The top one, the first one, f is qua. And the second one is perfect. Okay. With these two functions, we can create their sum, their difference, their product, and their ratio. So let's create the sum. Here's the notation for the sum. F plus g of x. This is the name. This is like f of x. But since it says f plus g, it tells me exactly what to do with those two functions. That's why this is a useful notation, f plus g of x. What does this mean? What do you think we're going to do to get this? We're going to write f of, what do you think this means? F of, yes? Plus g, exactly. That's exactly what it means. So that's why we use this name. So it tells us clearly what to do. So if we are asked to find f plus g, I know I have to add f to g. Now I'm going to replace them with the functions that we just created. And that's it. We created a new function by adding those two. So then f plus g of x is 3x squared plus 2x minus 7 and plus 2x minus 4. This piece is f of x. This piece is g of x. I'm sure you remember this from the previous class. So this is 3x squared. Now I add and combine like terms, plus 4x, and then I have minus 11. What does this represent? Let me give you an example. Let's suppose you have two different locations of your business. How will you determine the profit, total profit? You're going to add the profit that you get from the first business. Let's say it's in Washington, D.C., and then you're adding the second profit. That is a business in Baltimore. That's an example of a sum of two functions. Okay, now we can create a difference. What do you think this means? Because I have to write the definition first. What will this mean? That's it. Common sense, very good. Now I have to be very careful how I replace them. I replace the first one, but I have to subtract the second one. So what do I have to do? Can anyone dictate? Say it again. Yes. So what do I write? Very good. So now I combine like terms. These two go away. 3x squared minus 3. What does this represent? Well, it's the difference of those two functions. The third possibility is the product. The name of the function is fg of x. What does that mean? What do I have to do? Because I have to write the definition. Absolutely. F of x times g of x. Now I replace them. It's a totally different operation. I have to simplify if I can. Let's distribute. I prefer, but this is my preference. You can choose yours, of course, or mine. I prefer distributing from the binomial instead of the trinomial, but that's me. 2x times 3x squared is 6x cubed. 2x times 2x is positive 4x squared. 2x times negative 7 is negative 14x. Negative 4 times 3x squared is negative 12x squared. Negative 4 times 8x times 2x is negative 8x. And negative 4 times negative 7 is 28. I will try to combine like terms and see if I can. Yes, I can. 6x cubed minus 8x squared minus 22x and plus 28. What does this represent? It's a new function, totally new function, that represents the product that was obtained by creating the product of those two. Final function here is f over g of x. It's the ratio. Now, we did not say this when we created the sum, the difference in the product. But here I'm going to say if what? If what? Of course. We can get away from what we learned so far. Thank you. So, can anyone dictate what would this mean? So the top is 3x squared plus 2x minus 7, and the denominator is 2x minus 4. If I'm forced to put the if in there. If what? Good, which means when x is, only if x does not equal perfect. So then the domain of all these functions that we created, since they're all polynomials, will be, what is the domain of this and this and this? All real numbers. However, this one does not have all real numbers as domain. What is the domain of this function? And let's write it for the last one. Can anyone dictate the domain of the last one? This is part of chapter 4. Forgive me, this is part of chapter 3. So that's why this is very important now, because we're getting close to starting chapter 3. So for this function only, I would like to determine the domain.
So,
This is the domain of the rational function. It cannot have, we cannot plug in 2. Before we choose another example, and before I show you the last method, I would like to talk about the common domain. I'm going to create 2 graphs to illustrate what common domain represents. So here's the graph of a function. And let's say it goes from -5 to 3. I'm going to call this f. And let's say this is another function. That is this. And this is function g. Now I would like to ask you to find f plus g of 0. What does this mean? Forget about the graphs. What does this say to us? It says f of 0 plus, perfect. Can I determine them? Sure. So I'm going to put some numbers here. I'm going to say this is 1 and this is -4. So f at 0 will be -4 and g of 0 will be 1. So the answer will be -3. Now I'm going to ask you a different question. Here's my next question. I would like you to find f minus g of 4. What does this represent? Forget about the graphs for a moment. What does this represent? What do I have to do? Awesome. So I look at f of 4 and I realize what? There is no f of 4. Why? Because the domain of f is right. I can determine g of 4, but I cannot determine f of 4. The function is not defined there. So we cannot determine this. We have to stay within the common domain. Can anyone give us the common domain of these 2 functions, where they both exist at the same time, and if I'm asked to find their sum difference product and maybe quotient, I can. Where is the common domain? Exactly, between 0 and 3. That's where both functions exist. If I ask you anything outside of this, you're not going to be able to determine one or the other or both. So the common domain for this is 1, 3. So now you can say this to me. If you want me to evaluate the sum difference product quotient, make sure that you choose an x value between 1 and 3. If you choose to the left of, I'm sorry, 0. Sorry. If you choose to the left of 0, I won't be able to give you the answer back. If you choose to the right of 3, again, the same thing. Very good. Let's look at the last type, which is the last possible way, which is a more sophisticated way of determining new functions. Adding, subtracting, multiplying, and dividing is not a big deal. But this is different. and it's called function composition. So f comp g, let's write how we read it. F comp g, or you can say the composite of f and g. In short, f comp g. Let's look at three bubbles before we identify what this means. And let's say I start with an x value, x equals 3. I apply, which of these two functions is the closest to x? It's a silly question. G. So I have to apply g first. And that will be called the inner function. Not because it's closer to x, but because it has to be applied first. So g is the inner. What do I get? When I plug in 3 in g, what do I get? What did we do here? F plus g of 0, we said f of 0 plus g of 0. So now I'm telling you that g is applied to 3. What do we get? Of course, that's what we get. I don't know what number that is, I don't care. But what do you think we're going to apply to this number now? So we apply the inner function, and we got g of 3. And then what will happen next? To this number, whatever, 7. To this number, I apply what? Indeed. Which is the outer function. So this is the inner, because it's applied first. And f is the outer, because it's applied last. What will the answer be now? Think for a moment and tell me what will be the answer. And then that is the result of f comma g. It has to be f, but of what? Exactly. So in other words, we're putting a function inside another function. So knowing that, how will you present f comma g of x then? What does it mean? It means this, but with x instead of 3. So how do I write it? Not times. There is no product, sum, difference, quotient. F of g of x. So not to be confused with the sum, difference, product, or ratio. Okay? So this is what it's called function composition. What if I have this function that I'm asking you to create? F comp f of x. What will you say this means? That's it. I plug in f inside f. Last one. What about g comp f? How will I write this? That's it. Now, the concept of domain here is not the common domain. It's way more difficult, and we don't present it in this class. So in order to create function composition, the two functions do not have to have a common domain. What has to happen? I'm just going to tell you what has to happen. So what does this set represent for g? I don't know anything else, but g is applied to these. What is this set? How do we call it? We know its name. We talk about it all the time. The x values for g. What is this set called? Domain. Good. So this is a domain for g. Agreed? Because I apply g to these numbers. Okay, forget about the rest. What does this set represent for g? It's where the output of g is. So how do we call it? Perfect. So this is a range of g. Forget about g for a moment. Now tell me, what does this represent for f? Exactly. So this is also the domain of f. So here's the potential problem. What is the potential problem? I bring a number here, like g of 3, that I cannot apply f to. And the chain is broken. I cannot create the function composition. So the range of the inner function has to communicate well, or be the same, or whatever, with the domain of f. If this set does not represent values that I can apply f to, then the chain is broken. So it's not the concept, or you're not going to be asked to find the domain for the function composition. But I just want to make a point. The concept of common domain means nothing for the function composition. Only for sum addition, sum difference product ratio. Not here. Here the problem is this. The range of G has to work well with the domain of F. Otherwise, we cannot create a function composition. Okay, so let's look at a couple of problems with function composition. Let's say 55. This is 55, and the page is 310. And we are given f of x equals 4x minus 3, and g of x 5x squared minus 2. And in this problem, we're asked to find f comma g, g comma f, and then evaluate them at what? At 2. So 4 questions here. First question, find f comma g of x. Second question, find f comma g of 2. No problem. Once I have the function, I can plug in 2. Next question will be g comma f of x. And then once I have the function, I will plug in 2. So let's start with the first one. F comma g. I have to write the definition. What is the definition of f comma g? It's f of g of x. Awesome. I have to start with the inner function. You don't have to erase that. I'm just making a point. I need to replace this by what? By g. G is 5x squared minus 2. So this is f of 5x squared minus 2. Now I look at f. Let's go back and look at f and understand what f is telling us to do. F says 4 times minus 3. So please dictate. How do I write this? That's it. That's exactly what it means. That's exactly what f is telling us to do. 4 times whatever minus 3. I have to distribute. I get 20x squared minus 8 and minus 3. And the simplified form is 20x squared minus 11. I have f comma g. How will I determine f comma g of 2? Exactly in the given function, in the function that we just determined. So this will be f comma g of 2, which is, can anyone dictate what to write first? Very good. 20 times 2 squared minus 11. So 2 squared first is 4. 4 times 20 is 80. 80 minus 11. Is it 69? And it's done. Let's look at the other one. So this was determined, this was determined. Now we want to find g comma f. What does this mean? Very good, indeed. G of f of x. Again, I'm just making a point. I have to start with the inner function. What is the inner function now? This one, right? So this one is the 4x minus 3, and I have to write g of 4x minus 3. But now I have to stop and look. Let's take a look at what g says. G says to us, g of whatever is 5 times whatever squared minus 2. Okay, so please dictate. 5. Very good. Good. Now I have to think again, because this is what we've done on the first day of classes. Can you foil? Yes. Will you get full credit? Yes. I'm trying to make sure or help you move ahead and not foil again, if possible. But it's fine. So first term squared. X, good. Minus 2 times 4 times 3. Or you can say 2 times 3 times 4. It doesn't matter. So 2 times 3 is 6 times 4 is 24x plus the second term squared, which is and minus 2. Only now I can distribute 80x squared minus, I think this is 120, and this is 45 minus 2, which is 43. And this is the function composition of g and f. Now we are asked to evaluate it for 2. So g comp f of 2. Once I have the function, I don't have to do anything else but plug it in. So how do I write this? Very good. 80 times 2 squared minus 120 times 2 and plus 43. So 4 times 8, 320, minus 240 and plus 43. So these two will be 353 and 240. I got 113. Correct me if I'm wrong. This is the way we determine the function composition. It's a different